So the other day I told you about what is optical activity of solutions when a plane polarized light, which is generated by Nicol prism, is passed through a solution uh, which contains maybe optically active or inactive solution. In case if the light comes out of it without any deflection, we say the solution is optically inactive. If it is getting deflected and making an angle theta in the clockwise direction, we say it is optically active and dextrorotatory. While if it is making an anticlockwise direction deviation, then it is levorotatory solution. Optically active solutions must rotate plane polarized light, and if at all they are stereoisomers which are optically active, right? If it rotates in clockwise direction, we call it as dextro, and anti-clockwise direction we call it as levo. If one, for example, makes a dextro rotation of an angle theta, it will make an rotation of minus theta if you talk about its mirror image. And this 1 and 2 are called as enantiomers of each other. Any two stereoisomers which are non-mirror images, okay, if we compare about two stereoisomers which are not mirror images, then that is diastereomers. Cis and trans are diastereomers of each other. Now you can notice that here in this case, 3 and 4 structures, they are not exactly mirror image of each other. If they are not mirror images, then they are diastereomers. Okay. Next, you can see molecule have multiple chiral centers but possess a plane of symmetry within the molecule. Then such isomers are called as mesomers or mesoforms. See this example. In this case, this is an erythrose where we have OH and OH on the same side. Got it? But there is a plane of symmetry passing through that. Correct? If you have a plane of symmetry, then taking a mirror image will only make it to be superimposable. This I showed you the other day. Like this structure would be in superimposition. I mean, this structure, if you notice, is exactly same as this structure. So, which means they are superimposable and they are identical in nature. Hmm? See, the rotational operation cancels off due to the opposite and same magnitude of rotation, and this is called internal compensation. Okay. Now notice, if you have been given, four compounds and you're supposed to compare whether they are what type of stereoisomers, are they mesomers or enantiomers or diastereomers, we should be able to say. Now, for such cases, we can always use the logic that the vertical line, the groups on the vertical line should be same. Then you start comparing left and right. So let me take A as the reference and I will not change that, but try to bring B similar to that of A. So what I can do, see, I'm talking about the compound B now. In the case of B, the methyl is already intact because I require methyl on the vertical position. So here methyl is already there. So I will not disturb this H and OH. But I need to make sure that this ethyl comes at the bottom position here. And you know that we need to perform always two exchanges to get the identical molecule. So what would I do? I will put ethyl here and OH here. That is exchange number one. OH here and H here. That is exchange number two. So basically we have now H, OH and ethyl. So this is also B. This is also structure B. Got it? So I'll keep it aside. Similarly, let me work out on C also. So when it comes to C here, the methyl is already in its right position. H, OH, I need to bring the ethyl down. So ethyl here. So again, OH on the right, H on the left. This is what we need to perform. Okay. This will be compound C. Next, if you have to compare D, so see, in the case of D, methyl is again on the same position, so we will not disturb anything on the methyl positions here. Ethyl, if at all I bring it down here, then OH will be on the right, H will be on the left, because I need to make two exchanges. So that will become D. Now, once you have set B, C, and D very similar to that of A, especially the vertical line is same now. Now you compare how they look like, otherwise A and B, they doesn't look to be mirror images. So what are these two? These are diastereomers. So first one is being diastereomers. Next, A and C. A and C. In fact, B and C are both identical. So this will also remain diastereomers. Next, A and D. A and D, if you look, they look exactly same. So they are identical. They are identical. B and C are also identical. Just now we have learned identical. B and D are diastereomers. C and D are also diastereomers. This is what you would get. Okay, this is how you can compare it. Clear? Next, notice the other cases here. If you have A, B, C, D, E, and now I am supposed to compare them, what kind of grouping that is going to come across. I mean, whether they are enantiomers or diastereomers and so. Okay, so notice one by one here. So in the case of A, as you compare with B, now you notice that this methyl needs to be here, but in B position it is not there. Okay, so let me compare that part here. So I'll write down that B part, you know, which looks very similar to that of A. So I'll take these two lines here. Now this methyl H and OH are on the right positions, but this methyl has to come here. So I need to make two exchanges. So OH will come right, H will be here, and methyl here. So this is compound B. Now let's talk about C. In case of C, the positioning is all same. So I don't have to work out anything. C is perfect. C, we don't have to do anything. D, let's work on the D part here. So we have methyl here, H here, OH here. And now, if you notice these three, I need to perform even number of exchanges. So H here and OH here, right? So this is about D. Similarly, we need to work out on E here. So methyl, hydrogen, OH, up to this part it is fine. See the bottom part here, you can see I need to push the methyl down. So OH will come here, H will come here, and methyl will come here. This will be part E. Okay. Now let's compare AB everybody. You can check out A and B here. This is A and this is B. If I compare these two, this OH and OH are opposite here. They are on the same side. They are definitely not mirror images. That makes them as diastereomers. A and C, if you notice that they are exactly mirror images. OH here, OH here, OH here, and OH here. So that happens when you have a mirror here. So that means these two are enantiomers. These two are enantiomers. Next, A and D. A and D also has the same problem. They are not mirror images, so they are diastereomers. Next, B and C. This is B and this is C. Again, you can see they are not mirror images, so they are diastereomers. B and D. Now, here is an interesting part, everybody. B and D, they look like mirror images, but if you notice properly, there is a plane of symmetry passing through them, which means these are mesoforms. So mesoforms are both identical. They are identical, and they are meso. Okay. Next, C and D. C and D also makes it diastereomers. And D and E, D and E, same problem here also. You can see D and E, both of them makes it mesoforms and identical. These are identical and mesoforms. I hope this example is clear, everybody. Yeah. Now, my point is you can either work out on the basis of identifying keeping the vertical uh, arrangement similar and then compare left and right. Or you can actually write the configurations and see whether whatever we have written is matching or not. Okay. So what I'll do, I'll try to figure out the uh, exact configuration of every chiral center. See, now notice one carefully one by one. This is a chiral center. With respect to this chiral center, if we put the CIP rules, so this group will be the first priority. Then this group will be the second priority. Methyl is the third priority, and hydrogen will become the fourth priority. So if such is the case, you notice that 1, 2, 3 is going anti-clockwise direction. If a least priority is on the horizontal line and anti-clockwise direction is given, that means it will become R configuration. So this is an R configured chiral center. Okay. Now similarly, let us figure out the configuration on the second chiral center. So you see that you will have this as first priority wise, this is 1, 2, 3, and 4. And now if you compare 1, 2, 3, it is moving anti-clockwise direction again. Anti-clockwise direction with 4 on the horizontal line makes it as R configured. So which means both the chiral centers are R configured in this case. Go to the second case here now. So with respect to this chiral center, so OH will be 1, this will be 2, this will be 3, this will be 4. In that case, you can see 1, 2, 3. This is moving clockwise direction. Clockwise direction makes it as S. Okay. And if I talk about the second chiral center, you have priority 1, then 2, then 3, then 4. Now you notice that it is going in anti-clockwise direction. Anti-clockwise direction will make it as R. Because the least priority is on the horizontal line, anti-clockwise direction will become R. So this is having S and R. Clear? Next, check out C here. In case of C, I'll go a little faster now. Check out 1, 2, 3. These are the priorities here. So 1, 2, 3. It is going clockwise direction. Clockwise direction make it as S configuration at this position. Now here it is 1, 2, 3. Clockwise direction. Clockwise direction will make it as S. So this will become S here. Next, here 1, 2, 3. So anti-clockwise direction. Anti-clockwise direction makes it as R. 1, 2, 3. Again anti-clockwise direction. Anti-clockwise direction makes it as S because now the least priority is on the vertical line. Next, here you can see 1, 2, 3. So 1, 2, 3. Clockwise direction. Clockwise direction makes it as S. And here 1, 2, 3. 1, 2, 3. Anti-clockwise direction which makes it as R. These are the configurations. And now, like how we compare above, let us compare the same thing below also. AB, AC, AD. How are they related to each other? CD and DE. So check out AB. AB, you can see the configuration of one is matching, the other one is not. which means that is diastereomers. A and C. If this is RR, the other one is SS. That makes it enantiomers. Okay. Next. A and D. A and D, RR is matching, but this is becoming RS. So that is, it makes it diastereomers. Next, B and C. B and D is SS matching, but here it is not matching. So again, that makes it diastereomers. B and D. B and D, you can see S is becoming R, R is becoming S. So in that case, it could be either a mesoform or it could be an enantiomer. But since it is a mesoform identified already, so that means this is meso and identical. Next, C and D. C and D again makes it diastereomer. D and D. D and D again makes it as mesomers, mesoforms. Done. So you can see all of that is matching what we did it earlier. So you could either simply check out the configurations and then do it, or the better technique is always try to figure out this way and then compare one by one. Okay. Anyone has a doubt with these cases, please do ask now. Yeah. Right. Now, what if I were to ask you what is the RS configuration for every case is given here? Like this, there is a chiral center in this case. So I need to find out the RS configuration. Then how do we figure out? Guys, you need to check one thing. In RS configuration, what is the important point we learned is that group should come, the horizontal group should be facing towards you, vertical should go away from you. So imagine that your eyesight is this way, then it all makes sense, because when you keep it in this way, as you start watching from this end here, now you notice these two here, COOH will come on to the right hand side and this double bonded carbon will come on to the left hand side. So how does it look like now? Now if you put it on the Fisher projection here, you will have COOH on the right, CH double bond CH2 on the left. That makes methyl up and Cl down. Let's put the priority here. Priority was, this is first one, second one, third one, and fourth one. Now you notice 1, 2, 3. It is going in anti-clockwise direction. The anti-clockwise direction makes it. If it is anti-clockwise direction, that means it is going to be S configuration. This is the way we can figure out. Now same way, if you compare this molecule here, right? See, OH is coming out of the plane, deuterium is going inside the plane. So you watch it from this end of the diagram now. As you start watching from this end here, now you will notice, you know, this side on the top carbon we have CH double bond carbon and so on. And the bottom carbon we have CH2 here continued with other carbons. Of course, these two are connected on the back end, but we don't have to worry about that. And now notice this, when you're watching from this end, OH is coming out of the plane, which means it is on the left side. And D is going inside the plane, that means it is on the right hand side. So D is on the right, OH is on the left. This is how it is. So now priority wise, if you notice, this is 1, this is 2, this is 3. So is it going 1, 2, 3? So it is going moving clockwise. So since it is clockwise, it is S configuration. So here this carbon is S configured. Now here also this part is a chiral center. Now on this side it is a chiral center. So methyl is coming out of the plane, which suggests that the hydrogen is going inside the plane. Okay, methyl is coming out of the plane. So this is how it. So again, you have to start watching from this end here, right? As you start watching from this end. Now, when you make the hydrogen inside, which means it is on the right hand side, methyl on the left hand side, so then this will become the top side. So you can see that the top side is this carbon having a double bond carbon with chlorine. The bottom side is a carbon having a double bond with OH. And now methyl is coming out of the plane, which means it is on the left and this hydrogen is on the right. So now if you put the ranking, so this would be 1, 2, 3, and 4. So now you notice 1, 2, 3 moving clockwise direction. Clockwise will make it as S configuration. Thus, this chiral center will be S configured. Okay. Now, if already in a Fisher projection given, just you need to put out the priorities here. So notice priority wise, this is carbon 1 and this will be 2, this will be 3, this will be 4. So 1, 2, 3 moving clockwise direction. Clockwise direction make it as R configured because the least priority is on the vertical line. Okay. So that's how you work out on the RS configurations, everybody. These are very standard problems from RS configurations. So you should be able to know that. Next. You must understand the term specific rotation, which means whenever you are uh, taking an optically active solution, there is a deflection of the plane polarized light, correct? Now imagine we are taking this solution with some conditions. That is, when 1 gram of a solution is being taken in a polarimeter tube, which is of 10 centimeters, okay, horizontal length for that is 10 centimeter, which is 1 decimeter length. At a standard conditions are being taken. Then notice this. According to Biot's law, the amount of angle that it is being observed, right, that depends upon the concentration. Because if not, I take it as standard 1 gram solution. And if I take some new concentration here, so that theta will depend on that concentration. And concentration here is written normally in gram per liter. Okay, how many gram per liter we are taking? Clear? So let's say I took 1 gram per liter here, that will become the concentration. Next, what is the length? Length is normally measured in decimeter cube. So if you have a longer length of the tube, then the theta will always be directly proportional to that length. So theta observed is proportional to concentration and the length. And theta observed is equal to some constant into concentration into length. So this concentration, I mean this uh, constant, which is specific rotation, will be equal to mu observed by C into L. Okay. So mu observed, I mean, if this is what you need to see how to calculate the alpha. If theta is 355 degrees and concentration is 2 gram per liter, length of the tube is 25 centimeters, then the alpha value, that is specific rotation, will be 355 by 2 into 2.5 because I need to express the length always in decimeter. Okay, that's how we'll get what is the specific rotation. All right, next. See, if a solution has only one enantiomer, right, and there is no mirror image that is contained in it, then the solution is called optically pure solution. If there is any percentage of mixture of enantiomeric form, then the solution is optically impure. In fact, if both cases the solution is optically active, except when enantiomeric pair has 50% each. If both of them are present in 50%, that means I took 50% of dextro, 50% of levo mixed together, then that will become an impure solution And in fact, what you will notice is the solution now becomes optically inactive. And such a solution which is optically inactive and contains 50% of D, 50% of L is called as racemic mixture. And this time racemic mixture, is optically inactive because of the external compensation, which means one molecule is trying to give dextro, the other molecule will try to give levo because both the angles are same. Hence, the overall deflection is not observed for the plane polarized light. Okay, and see, we use this terminology enantiomeric excess depending upon what is the percentage dextro and levo it is. Suppose if you have 100% dextro and 0% levo, then the percentage enantiomeric excess will be 100%, percentage racemized will be 0. If dextro is 80%, levo is 20%, then enantiomeric excess will be 60%. Got it? What does that mean? That means you can see 20, 20% of both can be, compensating each other in their angle. So 40% will not show any rotation. Only the 60% of the dextro rotation will show the rotation here. So 50% of D, 50% of L if you take, then there is no enantiomeric excess. Everything is racemized, 100% racemized and optically inactive. If it is 25% and 75, we can say 50% is left and 50% is racemized. I hope all of you understood what is enantiomeric excess means. When do we use it? Next. If a solution contains 25% of dextro, then find the observed rotation and percentage racemization given the pure dextro is 30 degrees. Okay. Now such type of questions are being asked, like, you need to figure out uh, uh, observed rotation and percentage racemization. So you should be able to figure out. Okay. Check it out. How much will be the observed rotation? Because if you have 100% pure dextro, we found that the rotation is 30 degrees, correct? But now how much we have? We have 25% pure. 25% solution contains 25% of dextro. So only this much dextro is present. Clear? So in that case, how much will be the rotation found? Now notice this one. You need to understand one thing, that is this the one which is see, if 75% of levo is present and 25% of dextro is present, right? That makes it 100% of the solution. Now notice that 25% of dextro, correct, and 25% of levo will cancel with each other. So what is left now? We are left with 50% of levo. 50% of levo is enantiomeric excess. Okay. And you know that if 100% dextro is 30 degrees, what will be 100% pure? 100% pure levo. 100% levo will be minus 30 degrees. Okay. So if 100% levo is minus 30 degrees, in that case, 50% of levo will give you how much angle? So that will be equal to 50 into minus 30 divided by 100. So which makes it minus 15 degrees. So we should get minus 15 degrees in case if this is the observed form. And how much is the percentage racemization? We just learned that percentage racemization is 50% because the other 50% is enantiomeric excess. Clear, everyone? So I hope you know how to use this kind of how to solve for these kind of questions. Done? Right. Next, notice the next objective is about identifying the number of optically active isomers and so. Got it? So see, suppose if there are n number of chiral centers, okay, and this is the case which I have taken. That is, this is a chiral center. Like this, there are n number of chiral centers repeated one after the other. Left hand side there is different group, right hand side there is different group. Okay, and if you have n number of chiral centers, then the total number of stereoisomers will be 2 raised to power of n. Okay, and number of optically active isomers will also be 2 raised to power of n. Let us put this as p. Okay, number of enantiomeric pairs will be total isomers by 2. By 2 means 2 raised to power of n minus 1. Number of diastereomeric pairs. Diastereomeric pair means first list out all the pairs. If you have p number of total optical isomers, so pc2, that will become the total number of pairs. Correct? So out of those total number of pairs, remove all the enantiomeric pairs. So the leftover will be diastereomeric pairs. Okay. So you can notice this example, for simple understanding, we have three chiral centers here. So three chiral centers, and left hand side, right hand side, I don't see any symmetry. Both of them are different groups. In such case, n value is 3. So which means number of stereoisomers will be 8. Correct. So total number of dash stereomers will be 8C2, which is 28. Minus how many enantiomeric pairs we have? We have 4 of them. So 24 pairs we have. So 24 diastereomeric pairs and 4 enantiomeric pairs we have. Total stereoisomers are only 8. Okay. The logic can be applied very similar to a double bonded carbon as well. So if you have a double bonded carbon of n number of times, which means we can have so many geometrical isomers. Left hand side, right hand side, the groups are different. So there is no symmetry. Then the total number of stereogenic units are n. Number of stereoisomers are 2 raised to power of n. Geometrical isomers are 2 raised to power of n. Notice one thing, I'm using a terminology stereo units or stereogenic units. Every unit represents the number of double bonds which can showcase the cis and trans isomers across them. If they are able to show cis and trans or any geometrical isomerism form, we call it as the stereogenic units. Okay. If the question is asked about number of stereo centers is centers across which we can get geometrical isomers or optical isomers. Okay. So in this case also, if at all there are n number of uh, you know stereogenic units, then number of stereogenic centers or number of stereo centers will be equal to 2n. Okay, because with respect to every carbon we can change certain groups and make it as cis and trans isomers. Same logic here also. If you have to find out the number of stereo centers, so check out centers across which we can get geometrical isomers and optical isomers. Seen here, this double bond does not show any geometrical isomers, but this will show. But this is also a center across which I can get stereoisomers. These two centers also are the cases. I mean, because this double bond. See, what do you mean by this centers? See, if you have C double bond C, I'd have two groups here like this. Let's say 1, 2, 3, 4. Correct? With respect to this carbon also, I can make cis and trans because I can push 2 here and 1 here. Or with respect to this carbon also, I can push 4 here, 3 here and make it as cis and trans. Thus, every center across which we can make a geometrical isomer or a optical isomer is called as stereogenic unit, a stereogenic centers. So therefore 1, 2, 3, total 3 centers. Unit wise, one is a chiral center, which is also a unit, and a double bond, which is also a unit. So how many units we have? 2. So stereo units are 2. Stereo centers are 3. Is the logic clear? So now the number of stereoisomers will be 2 raised to power of 2, which is 4. So that could be cis with R, cis with S, trans with R, trans with S. Okay. Now, if a question is asked like this, find out the number of stereogenic centers, units, and chiral centers. Okay. So first find out across how many double bonds and single chiral centers we can have stereoisomers observed first. So let us go one by one here. So starting with, I'll just mark it with the color here. So 1, 2, 2, sorry, I'll use another one. Uh, this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you may have noticed, these are all chiral centers. Okay. Chiral centers are over. Now let's mark about the double bonds across which we can get the cis and trans isomers. One, we can get it here, and here we do not get a cis and trans isomer, but we can still get optical isomers. Okay, these are the two positions which we can get it. So now if I were to ask how many units we have, so these are all the units we need to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So number of stereogenic units, if you compare, that will be 12. So total we found it as 12. So you can see 4, 4, 8, 9, 10, 11, 12. Right. Next, number of stereo centers. Centers. Okay. Sorry. First we'll put chiral centers. Number of chiral centers. Chiral centers we found it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So total we found it as 10. So number of chiral centers as 10. So now number of stereo centers. Stereo centers include chiral centers plus, you can see, with respect to this carbon and this carbon we can make cis and trans. With respect to this carbon and this carbon we can make optical isomers. Hence we can say plus 10, 11, 12, 13, 14. So total 14. So 14 stereogenic centers we have. Is that okay? Please do check. If anyone has any doubt, they can ask me now. Done. Now notice. Now here there is a chiral center. Here there is a chiral center. Correct. Other than that, if you notice that, check out this one is coming out of the plane. Let's say, imagine if it is coming out of the plane, then uh, this would be on the plane. Again, out of the plane. Okay, out of the plane here. This will be, the double bond will support it. The same thing. This will remain out of the plane. Correct. And now this double bond, I mean consecutive double bond will make it, inside or outside the plane. So my point here is, with respect to this chlorine, bromine, and hydrogen iodide, we can either have a cis and trans isomers, or we can have optical isomers, which means I can count this entire thing. So please notice one thing here. From here till here, I can count everything as one unit. So with respect to that unit, these four groups can showcase either cis and trans or optical isomers. So that you need to count it as one unit. So now if at all I've been counting stereogenic units. So that's one unit, plus there are two chiral centers. So total there are three units. While chiral centers, when it comes to chiral centers, there are only two chiral centers. Okay. And lastly, if we have stereo centers, so you can see this is one center and this is one center. So two, three, four. So total we have four centers in general, right? Clear? Okay. Units are three, chiral centers are two, stereogenic centers are four. Okay. And by chance, if I ask you number of stereoisomers, that will be 2 raised to power of 3. So that makes it 8. Everyone clear? Next. What if in the case, what if we have the cases where there is a symmetry being observed? Cases of symmetry. Please notice the cases of symmetry. That is, you have, n number of n number of chiral centers. But unfortunately, this side and this side groups are same. Okay. In such case, what is the formula do we apply? How do we get that? Simple. See, total number of stereoisomers, we need to use this formula. That is 2 raised to power of n minus 1 plus 2 raised to power of p minus 1. And p will be equal to n by 2 if n is even number of centers, chiral centers. And p will be equal to n plus 1 by 2 if n is an odd number. Okay, if n is an odd number. Is it always valid? Sometimes it may not work also, but check out the cases what do we have. For example, if you have, CHOH four times, which means there are four chiral centers which it has present. Okay. In case of these four chiral centers now, when n is equal to 4, number of stereoisomers will be 2 raised to power of 3 plus 2 raised to power of 2 minus 1. Okay. Why 2 minus 1? Check out how do we calculate P. P will be equal to number of chiral centers, which is 4 by 2. So that makes it 2. Okay. Number of optically active isomers will be 2 raised to power of n minus 1. Optically inactive is 2 raised to power of p minus 1. These are the inactive ones. So active isomers are 8, inactive isomers are 2. Clear? The same logic applies to even when you have a double bonded group. That means to identify geometrical isomers. So 2 raised to power of n minus 1 plus 2 raised to power of p minus 1. So p is n by 2 if it is even, n plus 1 by 2 if it is odd. Okay, so this is a typical formula that is to be used. Now, what if I give you some questions to, uh, we have to write and check whether it is correct or not. Please check this out. I'll take this example, which is very standard one. I have CHOH, which is three times, sorry, and here I have CH3 and CH3 here, like this. Okay. So now let's see what does this mean. We have three chiral centers like this. which is CH3, CH3. So I need to have OH groups on it, correct? So let me put this skeleton multiple number of times, so that we can write all of them more easily. Yeah, check it out. First one, we have, let's say, OH, 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 H, H, and H. And now I can write the mirror image of the same. This is the first thing I can write. Okay. Theoretically, I'll expect this to be 2 raised to power of 3, 8. This is theoretically. But due to symmetry, that is not correct. Hmm? Second one, if you have OH here, and next OH here. So mirror image wise, OH, OH here, and OH here. Right. Next, we have OH, OH here, and OH here this way. And same thing I can write OH, OH here, and OH here. This is again the mirror image of each other. Got it? Lastly, OH, OH here, and OH here, while OH here, OH, and OH here. Right? See, theoretically, we expect these 8 to exist. Okay? Theoretically. But due to symmetry, all of these 8 will not exist. Some might be identical as well. And that's what we are trying to figure out. Okay? Now notice the first case, everybody. Have you noticed that this is a plane of symmetry? This is a plane of symmetry on this mirror image. Since these two are plane of symmetry, can I say that 1 and 2 are identical? 1 and 2 are identical. Okay. Next. Here, if you notice, 3 and 4 are enantiomers. These are not identical at all. So these are separate. So these are enantiomers. So two different forms. Correct? Next. Have you noticed this again? If you compare this one and this one, again there is, you can see plane of symmetry passing, which means 5 and 6 are mesomers of each other, which means they are identical again. So 5 and 6 are identical. Next. Here we have 7 and 8. So 7 and 8, if you compare, correct? These are again looks to be enantiomers, right? So it appears like we have many compounds. Now there is a problem here. If I take this molecule here, correct? Take this, let me copy it here and notice this carefully, everybody. I take this around and rotate it like this. Okay. I rotate it around here this way. Now 2 OH on the left, 1 OH on the right. Have you noticed that it is already same in this case? Correct. So which means, of course, these two are enantiomers and these two are enantiomers. But unfortunately, this seventh structure and fourth structure are same again. So 4 and 7 are same, identical. Likewise, okay. Third and eighth are same. Eighth are identical. So even though these two are enantiomers, they have already been counted as 3 and 4. We don't have to consider them again. So in total unique or unique number of stereoisomers which we have is total 4 only, which is in which we have two different mesoforms plus one enantiomeric pair. That's how we got total four different groups. So which means I can take this one. I'll just mark it down now. One, two, three, four. That's it. Rest all are repeats only. Everybody understood? Very important question. Usually we make this mistake. Okay. See why I'm saying that. Suppose even if I use a simple formula and try to calculate, stereoisomer formula is 2 raised to power of n minus 1 plus 2 raised to power of p minus 1. So p is an odd number. Odd number means how many, sorry, n is equal to 3, which means it is odd number. For odd number, p calculation is n plus 1 by 2. So that is 2 here. So number of stereoisomers, what do we get here? Should be 2 raised to power of uh, 3 minus 1 plus 2 raised to power of 2 minus 1. So this is 2 raised to power of 2 plus 2 raised to power of 1. So which is 4 plus 2, 6. 6 is what we expect, but actually answer what do we got? We got as only 4. Okay, got it? So the formula to be utilized when you have, geometrical isomers, it works pretty fine. When it comes to optical isomers, right? For a small number of carbons, right? Of course, if you have some carbon in between these molecules, then definitely that formula is valid. But if you have consecutive three OH groups continuously like this, then you have to typically write and check. Usually, we can, for three chiral centers, you can have maximum of only four molecules which are different, and those are the stereoisomers. Clear? Let's see another one. Suppose if you have CH double, sorry, let me put it like this. CH3, CH double bond CH, CH double bond CH, CH double bond CH, and CH3. This is how it is present. So now check out how many units we have. 1, 2, and 3 units we have. Okay. Here I'm taking the similar case which has a symmetry. Okay. Okay. Which has 3 units here. So you can see we might expect another 4. No, this time the formula will be properly applied and it will match with the formula's answer also. For that, what I'm doing, I'll just try to put out the structures here, which is much easier to explain. Check out. First, this is one way I can explain, where you have double bond, double bond, double bond here like this. So which means this is trans, trans, and trans. All three are being trans position. Second structure being, one trans here, second one trans here, and third one being like this. Okay, and then this one like this. So what is this one? Now it has become cis. So trans, trans, and cis. Clear? Trans, trans, and cis. Okay. Next, if you have uh, cis, cis, and cis, all three being cis here. So like this, we have double bond, cis, double bond, cis, and double bond. So we have cis, cis, and cis, all three being cis. Okay. And next we have cis here, and then trans here. So this is trans, cis, and cis. This is different. Altogether, it is different now. Got it? Now, what are the other forms we usually expect? Because if we have three stereogenic units, we expect eight of them, but out of them, there should be uh, superimposability. So now, other three, what we can expect, other two which we can expect here is, see, first I can have cis, then trans, then again cis. This we didn't consider, cis, trans, and cis. Likewise, first I can have trans, first I can have trans, right? Then I can have cis, then I can have trans. So trans, cis, and trans. Correct? If you may have noticed up to this, they all are unique. They doesn't look like anything repeated. Now see when the things will start repeating. Okay? Things will start repeating if at all I take it something of this sort here. So I took this as trans here. Here I took this as trans. Uh, trans. Then I took it as cis and cis. Cis and cis. Cis and cis. Cis and cis. Clear? Trans, cis, cis. Okay. See, trans, cis, cis, if you take trans, cis, cis, which is same as cis, cis, trans, because now these two are identical. These two will become identical. Clear? Likewise, if at all I have cis, cis, trans, okay, cis, 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 trans I've already done. Trans, cis, cis, we have done it. Yeah. Now we have cis, cis, trans, trans. If I take one cis and trans and trans. So you can see first one being cis, then I took it as trans, then I took it as trans, cis, trans, and trans. So again, you can see these two are identical. Here, these two are identical. So therefore, symmetry will make it to have these two repeated ones. So these two are unnecessary. So 1, 2, 3, 4, 5, 6. These six are completely unique, non-superimposable. So here you can see 1, 2, 3, 4, 5, and 6. Okay. So these 6, 1 to 6 are non-superimposable. Impossible geometrical isomers. Got it? Formula wise also you will get 6 only. Okay. So that formula is thoroughly applicable in the case of geometrical isomers, but not in the case of optical isomers. Clear? Now, let me explain you the term. What is resolution? Resolution is a process used for separation of enantiomers, especially enantiomers. Okay. Suppose if you have this chiral center and I take a mirror image of it, these two are the enantiomers. Now notice, according to the according to the structural properties, if you notice, 1 and 2 does not have any two different structural identity. Both of them will have same structural features. Therefore, boiling point of 1 and boiling point of 2 will be same. Melting point of 1 and melting point of 2 will be same. Whether you compare density, viscosity, refractive index, every features will be same. Chemical properties will also be same. Only difference what you will notice is biological properties. Okay. Biological properties are the only differences which you will see in enantiomeric mixtures. Biological property means the way they react within the uh, human body or within the animal cells. How will they work? Got it? So two enantiomers work slightly differently. That's the only difference which you'll find for enantiomers. Now notice, there are three methods of separations. One is chromatography, crystallization, and diastereomeric mixture forms. These two, we have to do it. Sorry. Okay. One second. Sorry. Okay. These two, we have to do it. These two are to be done without any chemical reactions, but diastereomeric mixture form is via a chemical reaction form. Okay. For example, if you compare tartaric acid, okay, you see this, if I take dextrorotatory and levorotatory tartaric acids, this is racemic mixture. Okay. Now, our objective is to separate this tartaric acid. Then what will I do? I will take a pure form of a chiral center which has a hydroxide group on it, OH group on it. Then I react with this solution, right? With this pure form in acidic medium. As you react, the acids will convert into an ester form. So on this position, C double bond O, this group will get connected here. So this chiral center will remain S once, right? Here also it will remain S. So that means you will have S, R, R as three chiral centers in the molecule. Here we have S, S, S as the three chiral centers in this molecule. So SRR, SSS. There doesn't seem to be enantiomers, right? So that means these two are diastereomeric pairs. Interesting feature of diastereomeric pair is that in diastereomeric pair, boiling point, melting point, density, viscosity, everything will be different. So it's easy to separate them out. Okay. So pair of diastereomers can be separated out using fractional distillation. So by fractional distillation, this and this can be separated out. So now we got two things separated. Once you got separated out, you take this solution, react with NaOH. On reaction with NaOH first, you will be able to remove out this alcohol, convert into carboxylate, and that carboxylate on hydrolysis again gets back to the original tartaric acid. That and this solution will be separated. Now, once you get separated, again use fractional distillation. You can separate the alcohol and you can separate the pure form. That's how the pure form of the tartaric acid is separated out. Everybody clear? So this is the way to separate out the uh, enantiomeric mixtures or racemic mixtures. Everybody clear? This method is called as resolution. I mean, this is one of the methods for resolution. Okay. So if the question is given, I mean, you will find lots of questions in MS Sean and other booklets also. Which of the following can be resolved? If you see that they are chiral in nature, that means they can be resolved. So your objective in the question should be to check out whether they are chiral or not. Whether they are chiral or not depends upon whether there is any chiral center on it or not. Okay, that's the way to view it. Clear, everybody? Okay, so I want you to go through it once again. Please check out how the diastereomeric mixture goes around. Okay, let's just take a minute's break. I'll get some water and sorry, check out amine inversion here. In this case, this nitrogen having four different groups here, you can notice that when you have three different groups here with a lone pair, that is also counted as a chiral center, right? Now the chiral center problem here is, suppose if you expect that this is some R configured, correct? Right? And then you have some S configured here, right? So problem here is, let's say I have a lone pair here, correct? I have R1, R3, and R2. that makes it as, let's say, S configuration. If this is R configuration and that is S configuration. Problem is this R will never remain as pure form. This S will never remain as pure form. The R, even if you prepare, let's say this is a freshly prepared tertiary amine with R configuration. Within no time, it will become 50% of R and 50% of S on its own. Same way, if you prepare freshly prepared, tertiary amine with S configuration, within no time, it will turn into 50% of R and 50% of S. Why is this happening? See, whenever you have two, whenever the nitrogen with these three different groups are present, and when they start coming close to each other due to their lone pair repulsions, right? Like this. So if you have nitrogen with lone pair and three groups here, and another nitrogen with lone pair and three groups here, as they start approaching close to each other, right? So what happens that nitrogen will start making a planar structure first, okay? Because the lone pair will start losing out its hybridizing nature and converts into the pure form of it. So it will start becoming something like an sp2 hybridized nitrogen, a planar surface. So when you get a planar surface here, after a while, it will try to come back to either this form of the structure, which is dextro or R configured, or this form, which is levo or S configured. Chances are 50-50%. So 50% of this and 50% of this. Therefore, even though you may have started with pure form of this one, as it reaches to this intermediate, you might get 50% of this as well. Thus, it's very difficult to make any resolution or separation methods for these enantiomers. So they can never be remained as pure. They'll always undergo racemization. Now, see, if this nitrogen is a part of three-membered or a four-membered ring, okay, then inversion is less likely to occur. Thus, chirality is observed. For example, in this case, nitrogen is there, lone pair is there, methyl is there. But this side, you can see it's very difficult to make this inversion anymore, because at this angle it cannot make an sp2 form like this, because for this to make it has to come out 120 degrees. That is not possible with this kind of angle. Therefore, when you have three-membered ring, you can have this as a chiral center. In fact, even this also as a chiral center. Same way, this as a chiral center as well as this as a chiral center. Got it? So three-membered and four-membered ring, you will not observe amine inversion, but here this could still be undergoing inversion. So this could still be undergoing amine inversion, but this side is a chiral center that can take care of it, achirality. So during the flipping or the inversion of amines, basically the potential energy changes like this. Molecule goes to an transition state where it becomes sp2. From there, again, it will come back to the other stage. But if one is R configured, the other one will be S configured. But in acidic medium, let's say I have an achiral molecule. In acidic medium, it will become chiral, correct? And that can be resolved because now the lone pair completely takes over the H plus and now it will be like a normal chiral center. So for such a chiral center, resolution is easy. Okay. Next, molecules which does not show flipping or inversion in this case. See, definitely three-membered ring will not show, four-membered ring will not show, correct? Here, because of this, you are seeing that there are two chiral centers, but it is a chiral molecule. But flipping is observed with respect to nitrogen here. Phosphorus, is bigger in size, so they do not have this flipping nature. So this can still be chiral. Sulfur with four different groups, including one lone pair, is also always chiral. Arsenic with one lone pair and three different groups is also always chiral. So the problem is only with nitrogen. Okay. Otherwise, even it's simpler groups with phosphorus or sulfur, they always remain chiral. Next, except for the second period elements, other atoms show chirality due to four different groups in the chiral centers. So only carbon nitrogen has this problem. When they have lone pair, they undergo inversion. But if it is phosphorus, sulfur, chlorine, arsenic, antimony, any of these cases, they all will show chirality. Okay. Next one. Check out structural chirality. Structural chirality is when you have the molecule itself is structurally aligned, such a way they are chiral. For example, octene. Octene in a trans form does not have any plane of symmetry. It does not have any center of symmetry. Thus makes it as an overall molecule it is chiral. Okay, but in the cis form, it will be always achiral because there is a plane of symmetry. Next note is adamantane. In case of adamantane here, correct? If you have these groups here, now notice this carefully. If the question is asked how many chiral centers, you can say this is a chiral center, this is a chiral center, this is a chiral center, this is a chiral center. So there are at least four chiral centers present in this case, correct? But does that mean it can show 2 raised to power of 4 enantiomers? Answer is no. Okay, it is only one. Reason being, at these positions you cannot have multiple orientations because they are all at the bridge positions. If you try to remove this methyl group, and where do we locate? We do not have multiple locations. We have to put it on the same place, which means there are, for if this molecule is given and been asked how many maximum number of stereoisomers we can have, so answer in that case is going to be only 2. So this and its mirror image, that's it. Clear? This and mirror image, correct? So the maximum number of stereoisomers will be only 2. Got it? I guess all of you have an understanding on this. How do we get the maximum number of stereoisomers in this case? Clear? See, even if I put any other another example, let's say if I put it in any cyclic form, doesn't matter. Like this, I have this way. I have a methyl group here. I have a methyl group here. I have a double bond here, methyl group here, and I have another methyl group here. Correct? Like this. Now see the number of questions I can be framing here. Number of chiral centers. Okay, let's go. Okay. Number of chiral centers. How many we have? 5 minutes. Okay, 5 minutes. So number of chiral centers, if you notice, we have one, two, three. So there are total 3 chiral centers. But number of stereoisomers, how many we can have? Now notice one thing. This is a separate chiral center. That and along with this entire molecule of this structure, that will also give you stereogenic unit. So that's why it will be 2 raised to power of 2. Now the answer is 4. Got it? Now you can't say 2 because this also there is here also there is a chiral center present on it. Hmm. Here, everybody, right? These are the types of cases that you need to go through. Now, let's take a few questions. How do we need to typically solve uh, any number of chiral centers, stereoisomers for those kind of cases? Here, we start with that 1 second. Okay, think. Let me give you a few questions on that. See, first case, if you have structure like this, we have OH, then we have CH, double bond CH with Br. Okay. Now we need to find out number of stereogenic units. First question, how many units we have? Next one is stereo centers. How many we have? Okay. Number of enantiomeric pairs. Okay. 1 second. Number of enantiomeric pairs. How many we have? Correct. Next, total number of pairs. Total number of pairs. How many we have? Got it. And number of fractions. That means how many number of fractions will come out of fractional distillation. Clear? So lastly, total number of stereoisomers. Okay. In fact, you need to know the number of stereoisomers to answer all of those questions. So I'll put it here first. So everybody, let's try it together. How do we solve these kind of cases? So number of stereogenic units, if you compare, you can see how many we have. 1, we have 2, right? And 3. So total we have 3 units. Stereogenic centers, if you compare, 1, 2, 3, 4. These 4 are centers. So total 4 centers we have. So number of stereoisomers, how many we will have? There is no symmetry here. So simply 2 raised to power of 3. So 8 we have. Okay. So how many enantiomeric pairs we will have? 2 raised to power of 3 minus 1, which is 2 raised to power of 2, which makes it 4. Correct? So there are 4 pairs we can have. Total number of pairs, we have here is 4. Correct? Sorry, total number of pair means 8C2. These are the total number of pairs. Correct? So which is 24. And total number of fractions. How many fractions we can have? Now, since we have 4 enantiomeric pairs, correct? What kind of compounds we can have? So check it out. First, here these two are chiral centers, and this one will show cis and trans isomers. So first I'll put it like this: cis, 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 cis. 4 cases we can have cis. 4 cases we can have trans, like this. So here I can have cis RR, cis RS, cis SS, cis SR, like this: trans RR, trans RS, trans SS, trans SR. Correct? Now you can see these two are one pairs. These two are one pair. Sorry. These two are one pair. These two are one pair here. Similarly, these two are one pair and these two are one pair here, like this. So total we have 4 such pairs. Correct? Now, of course, I cannot separate the pairs, right? This and this we cannot separate out. This will be coming out one fraction. These two will come out as one fraction. These two will come out as one fraction. These two will come out as one fraction. So total how many fractions you will come out across? So 4 fractions. By chance, if the question is also asked how many number of diastereomeric pairs we have. Diastereomeric pairs. See, diastereomeric pairs includes total 24 pairs, out of which 4 you have to remove out. Those are enantiomeric pairs. So total 20 diastereomeric pairs. Everybody clear how to solve these questions? Any doubt? Everybody, right. Next question would be about uh, identifying the isomers, based on the reactions given. So, reaction based isomer questions. Let's see. Reaction based isomer questions. So, in this case, what we'll try to do is monochlorination monochlorination of the following compounds, and using the monochlorination, right, like this we have, and then monochlorination Cl2 and H nu. We need to figure out all these questions, that is number of structural isomers, how many structural isomers I can get, clear, or number of isomers, total isomers, including including stereoisomers, how many we can get. Next, number of optically active how many we have, and lastly number of fractions, that means how many fractional distillations, how many number of fractions we can get during fractional distillations. These are the type of questions that can be asked. So check it out. So in the first case, you know always try to draw the original structure like this. So usually you can have some skeletons. First write down few skeletons like this, and now keep chlorine distributed at different positions. So how many different ways we can get? See, chlorine here or chlorine here. Don't you think these two are one and the same again? So these two are repeated structures, correct? So this is done. So here is the chiral center. Got it? So therefore, I will count this as only one isomer. Here I'll count it as two isomers. Structurally, there are only two isomers, including stereo, total three isomers. Optical isomers are two. Number of fractions you will get as two. Why? Because this is an enantiomeric pair. You cannot separate it out. So this and this can be separated. So only two fractions we will get. Okay. Here, I hope all of you got this. The next one, I'm expecting all of you to try it out on your own now. Okay. So this time I'm just increasing the number of carbons here. So make it as 5 carbons, Cl2, H nu. The question is the same. You need to figure out all of these cases. Number of structural isomers, stereoisomers, optical isomers, and fractions. Okay, please do that, everybody. Please try it out. Notice, check if you may have got this cases. So first, I'm putting few skeletons here. I don't think you require more than 3 skeletons. Then one chlorine here, one chlorine here, and one chlorine here. These are the three cases we can have. Here there is one chiral center. So this you will count it as one isomer. Here you count it as two isomer. Here you will count it as one isomer. Structurally, there are three, including stereo, there are four. Optically active two, number of fractions three. Got it? This is what you should get, everybody. Check if you have got that. Right. See the next one. Next one is similar lines. If you have 2,3-dimethyl butane, correct, in the presence of Cl2 and H nu. Again, if you have to work out on the same kind, you will get only two skeletons here. We require two skeletons here. In one skeleton, chlorine will be here. In one skeleton, chlorine will be here. These are the two possible ones. Correct? You can see in this case there is a chiral center, so which makes it at 2. Here there is no chiral center, so 1. And number of structural isomers, if you compare, we have 2, including stereo 3, optically active 2, fractions 2. Okay, you keep it there. See. Everybody? Now I'll go a little bit more detailed case. Now try this one. For this, if at all we react with Cl2H nu, okay, I need to find out all these cases, number of structural, including stereo, active, and number of fractions. Everyone, please try this out. Right, please check if you got these cases, everybody. So first one, I'll put out few skeletons here. I think 4 skeletons are enough for this one. So I can start chlorine from here, 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 and here. So it covers all the structural cases. So structurally you can have 4. Now you notice that there is a chiral center here and one more case chiral center here. So here I'll count it as 2 isomers, 2 isomers, 1 isomer, and 1 isomer. Total of 6 total isomers here, optically active or 4. Now fraction wise, this you will count it as 1, this you will count it as 1, 1 and 1. Total 4. So 4 fractions is what we should get. Okay. So I guess this is clear, everybody. Check if your answers are matching. Right. Let's do the next case here. This time instead of having methyl, I have bromine. That's the only difference we have. So F case, I'm changing a bit. Yeah. So let's talk about case E. Again, I'll have very similar skeletons here. So I'll just copy these cases because we are writing the same skeletons here, except that we have uh, bromine also present. Correct. So here we already have a bromine group on it. So I will write this as bromine here, bromine, bromine, and it's not here, but chlorine can be at this location. Chlorine, correct? These are the monochlorination of halogens. Okay. Now notice one by one. When you have bromine, this is a chiral center here. Now we have two chiral centers here. Now here we have one more chiral center here. Here again we got one chiral center. So here I'll count it as 2 isomers. Here I'll count it as 4 isomers because there is no symmetry as such. So here I'll count it as 2 isomers. Here I'll count it as 2 isomers. Okay. So structurally there are only 4, but stereo, including stereo, if you notice, we totally we got it as 10 different isomers. Optically active, all of them. Fractions, very important, everybody. Out of these four, you will count it as only two because these four are basically two enantiomeric pairs. So one pair, two pairs can be separated, but within the pair we cannot separate. So two here, one, three, four, five. So total how many fractions we'll get? Five such fractions we can get. Okay. Next, check out F. We have bromine here. Okay. And now I'm doing chlorination on it. This time, bromine already has a fixed configuration. Imagine I told you that bromine is R configured here. I mean, sorry, the chiral center is R configured already. If that is the case, you need to realize one thing, that when such case is been given to you, here, let me first write down the skeletons. In such case, as long as you do not disturb this chiral center, right, the the configuration remains constant. It will not be disturbed there. Clear? It will be disturbed only when the chlorine comes at that position. So which means first one is chlorine here, second one is chlorine here, third one is chlorine here. Only when the chlorine comes at that chiral position, only when it comes at that chiral position, right? That is when you will have the uh, chirality of the bromine lost. Otherwise, the chirality will not be lost in all the cases. It will remain R. So here it will remain R, it will remain R, R like this. Correct? Not R, basically, I mean, R is not a correct word to use there. I meant the configuration will be there. There will be some configuration which is fixed configuration. It will not change. Now, since it's a fixed configuration, it is a chiral center, but the configuration is fixed. Hence, you will read it as only one isomer. You do not read it as two isomers. Now, we got a new chiral center, but the other chiral center is present, but that configuration is fixed. So, therefore, you will count it as only two isomers. Okay. If imagine this is R, here we will have one R and R, the other will be R and S. Now, here it is a fixed configuration, although it is a chiral center, I'll count it as 1. Here there is no fixed chiral center, so now this time I'll count it as 2. Got it? Now notice one thing here. Clear? So how many structural isomers we got? 1, 2, 3, 4. So 4 structural isomers we got. Including stereo, how many I got here? So 2, 4, 5, 6. So total we got 6. Okay? Total we got it as 6. And how many optically active isomers? If you notice, all of them are optically active. All 6 are optically active. How many fractions you got? Now notice very carefully. This is one fraction. And here there are two fractions, everybody. Why two fractions? Now these are diastereomers. These are not enantiomers anymore. So these two are diastereomers. Now this is an enantiomer. This is only one. And here these are enantiomers. These cannot be separated. So how do I count? 1, 2, 3, 4, 5. So again, fractions you will get it as 5 here. Got it? Important case, everyone. So here we will have 5 fractions. I hope all of you got that. Right. Now see the third case here. We need to find dichloro derivatives now. Okay. Find dichloro derivatives of the following. First one being propane. Okay. So if propane is going through dichloro, Cl2 H nu. So we can have two chloro like this. We can have two chloro like this. We can have two chloro this way, and we can have two chloro like this. This is the way we can have dichloroform. Correct? So again, if you try to figure out all these parameters, number of structural isomers, how many we can get? Four of them, including stereo. Here you can see there is a chiral center, so that makes it five of them. Optically active, how many we have? Two of them. Fractions, how many we have? Four of them. Okay. Okay. Right. Dichloro case is clear. Let's see the second case. Please do it together. If you have cyclohexane and then we are using 2 moles of Cl2 and H nu, then how many such products we can get? First, write down all the skeletons. At least write 4 skeletons. If more needed, we can write it at the end. First, write 4. That should be enough. So dichloro. So which means we can have 2 chlorines here, or 2 chlorines adjacent to this one, or then alternative to here, and completely opposite to each other. These are the 4 forms we can have. Once again. Done. Then here we can have one. Right now, notice there are 2 chiral centers, but unfortunately there is a plane of symmetry also passing through them. Because of the plane of symmetry, we'll have one of them as mesoform, so you'll only count it as 3. Same logic goes here also. There is a plane of symmetry passing through this, although there are 2 chiral centers, so which makes it another 3. But here there are no chiral centers, but we can have 2 of them because of cis and trans isomers. So these two I'm writing it as cis and trans isomers. Okay. So cis and trans isomers includes 2 chlorine this way and 1 chlorine coming out of the plane and going inside the plane. So 2 of them. Okay. And now let's see what are these parameters says. How many structural we found? 4 of them. You can see 1, 2, 3, 4. 4 structural we found. How many isomers including stereo we have? See, total number of isomers include 3 plus 3, 6, 6 plus 2, 8 plus 1, 9. So total we have 9 of them. Optically active, how many we have? 2 here and 2 here. So total 4. How many fractions we can have? Here we can make 2, 2, 1, 5. Here we can separate both of them because they are cis and trans. So 7. So total 7 fractions we can have. Any doubt in this question? Please do ask everyone.
Yes, sir.
Yes, beta.
Sir, can you say about optically active, how it is for?
Yes, beta. See, in here, if you notice these 3 and these 3, here, let me write down those 3 structures all. Here, one chlorine like this, one chlorine like this one, and the other one it's mirror image, where chlorine is here and this chlorine is, these two are non-superimposable mirror images. And the third one being 2 chlorines coming out of the plane or 2 chlorines going inside the plane. This is one and the same. These two are identical and they are optically inactive. So this is optically active, this is optically active. Similarly, if you see the second case, one chlorine coming out of the plane and one chlorine going inside the plane. And similarly here going inside the plane and here coming outside the plane. These two are optically active. Samya, clear beta?
Yes, sir.
Right. Right. Last one. Let me just put this as an example here. Okay. So if a structure of this kind is given, which I told you earlier, like this, with double bond here, OH here, double bond O this way, and a methyl group here like this. Okay. So these are all the points you need to check it out. Number of chiral centers. Okay. Number of stereo centers. Number of stereoisomers. Number of enantiomeric pairs. Enantiomeric pairs. And number of fractions to separate them. How many number of fractions to separate them? Got it? And lastly, number of optically active. Right. So if you compare all of this, check it out. Where all this is one chiral center, chiral center, and chiral center. So there are four chiral center. Now, if you have to count stereogenic center, this one and this one need to be counted as well. So that makes it six. Stereoisomers, correct? You know that with respect to these two, we can have one unit. This is one unit. This is one unit. This is one unit, and this is one unit. So units are only four. So 2 raised to power of 4, which makes it 16. 2 raised to power of 4, which makes it 16. Number of enantiomeric pairs. How many we have? 8 such pairs we will have. Hmm? No, okay. And how many fractions we have? 8 such fractions we have. Got it? Number of optically active, how many we have? 16. All of them are optically active. Clear? Finished? Everybody? Right. I have covered almost all the basic cases which are essential for JEE, and all these cases have been asked in JEE already. Got it? And I think this